Hi guys, welcome to another lecture in the series General Inorganic Chemistry, and today we're going to be talking about measurements and conversions. And the content from this course comes from the text Chemistry, the Central Science 13th edition. So you would have been familiar with units of measurement. Basically, most of the things that you consume would have some amount of reference to the mass or the volume on the container. If we look here at this Coca-Cola bottle, we see here that the volume is measured as 355 mils. And so the units used for scientific measurements are those of the metric system. So we call them the SI units, which is from a French origin. So in 1960, an international agreement was reached specifying a particular choice of metric units for use in scientific measurements. So we're going to mention these 7 base units, but really the first 5 are what we mainly use in chemistry. So firstly, the mass, physical quantity mass, the name of the unit kilogram, and of course the abbreviation, a small k and a small g, or a common k and a common g. For length, we have meter and we have a common m. For time, we have second and we have a common s or sec. And for temperature, we have Kelvin and that's a capital K. For the amount of substance, and you will see this a lot, mole, the abbreviation common MOL. So with SI units, we see several prefixes, and they're used to indicate decimal fractions or multiples of various units. So for example, you will see milli, so we have milli in the table here, abbreviation common M, and it means 10 to the minus 3, right? So milli, as we said, it represents 10 to the minus 3 fraction. That's 1,000th of a unit. And so if you see milligram, we're talking about 10 to the minus 3 grams. Okay. And therefore, if you see millimeter, we're talking about 10 to the minus 3 meters. So you can just take a second and browse through the table. Look at what jumps out at you. Mega, giga, 10 to the 9, 10 to the 6. And you probably would have been more familiar with your kilo, which is 10 to the 3, deci, which is 10 to the minus 1, centi, which is 10 to the minus 2, etc. Right? Less familiar are the nano, 10 to the minus 9, pico, capital P or P, 10 to the minus 12, seen here, etc. Right? And just to mention micro, and that's the Greek letter mu, and that is the abbreviation for micro, and that stands for 10 to the minus 6. So KDCM mu NPFAZ. All right, so common letters here, and the capital letters are above here. All right, so the first unit we're looking at is length and mass. And so the SI base unit of length is the meter, a distance slightly longer than a yard. So the mass is a measure of the amount of material in an object. And so the SI unit for mass is kilo, which is the prefix, and then gram, kg, right? Which is equal to about 2.2 pounds. So if you go into the supermarket, you might see either kg or lb, right? And so we need to be familiar with the fact that, okay, or we need to understand rather that our SI base unit for mass is kilogram, and though we may see other measurements, we need to stick with the SI base unit. And of course, we will see further how we can convert between various units. All right, so this base unit is unusual because it uses a prefix kilo instead of the word gram alone, right? So you would think that if it's the base unit, then it would be gram, but quite unusual that the base unit is a multiple of something, right? Kg. So we obtain other units for mass by adding prefixes to the word gram. So our first question is, what is the name of the unit that equals A, 10 to the minus 9 gram, B, 10 to the minus 6 second, or 10 to the minus 3 meter? So pause, take a second, try to recall before you go back or proceed. All right, so if you had A as nanogram, B as microsecond with mu s, or C as millimeter mm, then you would have been correct. All right, so the other quantity that we're going to look at is temperature. So the temperature scales, commonly we see a lot in science are Celsius and Kelvin. The Celsius scale was originally based on the assignment of 0 degrees Celsius to the freezing point of water and 100 degrees Celsius to its boiling point at sea level, right? So we should have been very familiar with Celsius. However, we need to be able to convert between Celsius and Kelvin, right? And so here we see an equation. So whatever the value of the Celsius is, all we have to do is to add 273.15 to get the Kelvin. We also see, and particularly in the US, you will see Fahrenheit scale, and some of your appliances may have Fahrenheit scale, but we don't yet generally use this unit in science. And so water freezes at 32 Fahrenheit and boils at 212 Fahrenheit. And so the Celsius and Fahrenheit scales are related according to these two equations here. So if you have Celsius and you want to calculate Fahrenheit, or vice versa, if you have Fahrenheit and you want to calculate Celsius, you could just go ahead and plug the values in these two equations. So that leads us to another question, which says, a weather forecaster predicts the temperature will reach 31 degrees Celsius. What is the temperature in Kelvin and Fahrenheit? So I hope you took a second to write down those equations so you can make these conversions. All right, so for the Kelvin conversion, that's quite simple. All we have to do is to add 273 to the value to get the answer in Kelvin. And of course, we would have to plug the Celsius value in the appropriate equation to get the Fahrenheit. So we just plug it in, multiply it by 9/5 and add 32. And if you got 88 Fahrenheit, then you would have been correct. Now, there are some SI units that are derived. In other words, they have a combination of more than one unit. And so the SI base units are used to formulate derived units. A derived unit is obtained by multiplication or division of one or more of the base units, right? And so two common derived units that you will encounter in chemistry are those for volume and density. So I do hope that this is somewhat of a revision. So for volume, the volume of a cube is its length cubed, right? So the length of it, so here we see the length 1 meter, 1 meter, 1 meter, right? So the length cubed. And so thus the derived SI unit of volume is the SI unit of length m raised to the third power, which is cubed, right? And so the cubic meter is the volume of a cube that has 1 meters on each side, as we see here. So smaller units such as the cubic centimeters, and you will see, I'm sure this might jump out at you as something that you recognize, and sometimes you will see that as cc, right? So cubic centimeters, cc. So you will see that it's basically the same thing, are frequently used in chemistry. Another volume unit that we will see is liter. You will see liter, which equals a cubic decimeter, so dm cube. So if you have seen that before, 1 liter is equal to a dm cube and is slightly larger than a quart. And so you need to remember this conversion. 1 liter is equal to 1 dm cube. The liter is the first metric unit we have encountered that is not an SI unit. So there are 1000 mils in a liter, and 1 mil is the same volume as 1 centimeters cube, and that's the same as well, just to write it out, 1 mil is equal to 1 centimeter cube, right? So we just need to know these things, right? So a cc is equal to cubic centimeters, and we might see it written like this or this, and that is also equal to 1 mil, right? So we could see cc, cm cubed, or ml. They're all equal. And another thing that's equal is 1000 mil is equal to 1 liter, which is equal to 1 dm cube, right? So we need to remember these conversions. For density, right? Density is defined as the amount of mass in a unit volume of a substance. So density, mass per unit volume. And so the densities of solids and liquids are commonly expressed in either gram per mil or gram per cubic centimeters, right? So as we know from the previous slide that it's the same thing, right? So you will either see grams per milliliter or grams per cubic centimeter. All right, so for significant figures, and this is just revision and for you guys to know that whenever you do your calculations, you need to bear in mind the rules for significant figures, right? So we're going to take our time and go through these rules so that in the future, whenever we do any calculation, we need to make reference to significant figures. All right, so to determine the number of significant figures in a reported measurement, read the number from left to right, counting the digits starting with the first digit that is not 0. So in any measurement that is properly reported, all non-zero digits are significant. And so because zeros can be used either as part of the measured value or merely to locate the decimal point, they may or may not be significant. So let's go ahead now and look at some of the rules which govern whether or not these zeros are significant. All right, so the first rule is that zeros between non-zero digits are always significant. And so if we have a value such as 1005, the 2 zeros here that are between non-zero values are always significant. So here we count 1, 2, 3, 4 significant figures. we have another 0 here that is between two non-zero values, and so we have three significant figures, 1, 2, and 3. The second rule says zeros at the beginning of a number are never significant. They merely indicate the position of the decimal point. So 0.02 grams has one significant figure. 0.0026 centimeters has two significant figures, right? So zeros at the beginning of a number are never significant. The third rule is that zeros at the end of a number are significant if the number contains a decimal point, right? So once you have a decimal point, then the zeros that occur at the end of a number are significant. So here we have 0.0200. We have three significant figures here. So the two zeros are significant because we have a decimal point. Here, 3.0, we have two significant figures because, right? Because we have a decimal point. All right, so a problem arises when a number ends with zero, but contains no decimal point, right? And so in such cases, it is normally assumed that the zeros are not significant. In that case, we use exponential notation, and therefore we can indicate whether or not the end zeros are significant. So for example, a mass of 10,300 grams can be written to show 3, 4, or 5 significant figures depending on how the measurement is obtained, right? And so in this case, we can put a decimal, right? Which means that here we have three significant figures. So 1, 2, and 3 times 10 to the 4. So if you multiply this value by 10 to the 4, then you will get 10,300, right? So how we solve the problem of numbers ending with 0 is actually to put them in the exponential notation so that it has a decimal point, and therefore all of the zeros that come after the 3 in this case would be significant. So here we have 4 significant figures, and here we have 5 significant figures because these zeros are now significant because we have a decimal according to rule 3. All right, so our next question is, how many significant figures are in each of the following numbers? Assume that each number is a measured quantity. So take a second and look through A, B, and C and let me know how many significants are in each number. All right, so if you answered 4 for A, the zeros are significant figures, right? So that's A here. So 1, 2, 3, and 4. All right, so for B, 4 as well, the exponential term does not add to the number of significant figures. So we're counting here 1, 2, 3, and 4. And then finally, for the 5,000, right, for this one, we're saying that it has one significant figure. So we assume that the zeros are not significant when there's no decimal point, as we said before. If the number has more significant figures, a decimal point should be employed, or the number written in exponential notation Thus, 5,000 and a decimal point has four significant figures, whereas 5.00 times 10 to the 3, which works out to be the same thing, has three significant figures, right? So there are ways to get around this, right? So we can put a decimal point there to make all the zeros here significant. So we have a total of four significant figures, or we can change it to the exponential notation here. All right, so what about calculations, right? Yes, we're going through these rules, but we need to apply these rules, right? So for all of the calculations to do with moles or any calculation that we're doing, we need to employ the rules that we're learning here. So how do we apply significant figures in calculations? So when carrying measured quantities through calculations, the least certain measurement limits the certainty of the calculated quantity and thereby determines the number of significant figures in the final answer. So the final answer should be reported with only one uncertain digit. And don't worry if you don't get it yet, you will. To keep track of significant figures in calculations, we will make frequent use of two rules. One for addition and subtraction. So you have to look at whether or not you're adding or subtracting, or multiplying or dividing, right? So we're making that distinction here. You have to think and say, okay, am I adding or subtracting, or am I multiplying or dividing? Because different rules apply. All right, so let's look at it let's get some more clarity. So for addition and subtraction, the result has the same number of decimal places as the measurement with the fewest decimal places. Let me read that again. For addition and subtraction, the result has the same number of decimal places as the measurement with the fewest decimal places. And when the result contains more than the correct number of significant figures, it must be rounded off, right? So I hope you remember how to round off. Consider the following example in which the uncertain digits appear in color, right? So this is an addition, right? So we're adding three numbers together, and clearly they have different. This has two. The first one has two decimal places, that is 0.42. The second number has three decimal places, that is 0.322. And then the final one has one decimal place, 0.1. So what you'll do is that you will go ahead and do the addition. However, this number, which is this one, limits the number of significant figures in the result. So let's read here again. So for addition and subtraction, the result has the same number of decimal places as the measurement with the fewest decimal places. So here we're adding three numbers, and this is the number with the fewest decimal places, 1, as compared to 2 and 3. So we add them up as we would do normally, and then we round off to one decimal place. So our answer, final answer, should be rounded up to one decimal place, which is 104.8, right? So our answer would be reported as 104.8. So what is the difference with multiplication and division? Well, for multiplication and division, the result contains the same number of significant figures as the measurement with the fewest significant figures, right? So when the result contains more than the correct number of significant figures, it must be rounded off, as we saw previously when we were looking at addition and subtraction. So for example, the area of a rectangle whose measured edge contains, well, lengths are 6.221 and 5.2 centimeters should be reported with two significant figures as 32 centimeters squared, even though a calculator shows a product to have more digits, right? So if you plug in these values, both values in a calculator, and multiply them, this is the result that you will see on your calculator. However, because we have 5.2, which has the fewest significant figures, right? Our answer has to have two significant figures, and therefore it's rounded off to 32 centimeters squared, right? Because 5.2 has two significant figures, as we said, right? So if this value was greater than 5, then it would have been 33, right? So that's why we use the term rounded off. But because it is 32.3, then it's less than 5, and so we can work with 32. So notice that for addition and subtraction, decimal places are counted in determining how many digits are reported in the final answer. As opposed to multiplication and division, significant figures are counted in determining how many digits to report, right? And so for addition and subtraction, as we see here, we count decimal places, while for multiplication and division, we count significant figures. All right, so that leads us to another question, which says a vessel containing a gas of 25 degrees Celsius is weighed and then emptied and then reweighed as depicted below. So from the data provided, calculate the density of the gas at 25 degrees Celsius. All right, so this is the empty container, which has a mass of 836.25 grams. And then this is the container with the gas, right? So I have redrawn it, albeit not very well. We have gas plus container here that weighs 837.63 grams, the same as we see here. And then we have the empty container, 836.25 grams, right? And so that's important information. And the volume of the gas is given as 1.05 times 10 to the 3 centimeters cubed. All right, so go ahead and attempt to calculate the density. All right, so if you had this as your answer, which is 1.31 times 10 to the minus 3 gram per mil, then you would have been correct. The unit again for the density, gram per mil or gram per centimeters cube. All right, so how did we arrive at that number? So first we had to calculate the mass of the gas, right? So to calculate the density, we must know both the mass and the volume of the gas, right? And so the mass of the gas is just the difference in the masses of the full and the empty container, right? So we just subtract them and we get the mass of the gas, which is 1.38, right? So in subtracting numbers, we determine the number of significant figures in our result by counting decimal places in each quantity. In this case, each quantity has two decimal places, right? So 0.63, 0.25, and so our result also has two decimal places. So there's no difference in, least or most decimal places here, so we just keep it consistent. Thus, the mass of the gas is 1.38 grams, 2 decimal places, as I said. So using the volume given in the question and the definition of density, which is mass per unit volume, so we divide the 1.38 grams by the volume of the gas given, and we get this value here, which is three significant figures. And the reason why is that it corresponds to the number of significant figures in the two numbers here, right? So 1, 2, 3 sig fig, 1, 2, 3 sig fig, right? So our answer also has 1, 2, 3 significant figures, right? So we could write it either this way or that way. Either way, three significant figures. All right, so the next thing that we're going to talk about is dimensional analysis. And don't get too intimidated by this topic. It's really not as fancy as the title suggests. So in dimensional analysis, units are multiplied together or divided into each other along with the numerical values. Equivalent units cancel each other. And so the key to using dimensional analysis is the correct use of conversion factors. I cannot stress this enough. Conversion, you have to use it correctly, conversion factors, to change one unit into another. And so a conversion factor is a fraction whose numerator and denominator are the same quantity expressed in different units. Let me repeat that. A conversion factor is a fraction whose numerator and denominator are the same quantity expressed in different units. All right, so for example, 2.54 centimeters and 1 inch are the same length, right? So it's the same thing in different units. That's the conversion factor. So this relationship allows us to write two conversion factors, one with the centimeters as the numerator or it as a denominator. It doesn't matter. They are equal, so they cancel out each other. So we use the first factor to convert inches to centimeters. That's this one. And for example, the length in centimeters of an object that is 8.50 inch long is, so here, or what we desire, the unit that we desire is centimeters. The unit that we have is inches. So we have to multiply it by our conversion factor. And so in this case, because we're trying to get centimeters, it has to be the numerator in the conversion factor. And the unit that we're trying to get rid of has to be the denominator in the conversion factor. So we have to use this one, all right? And as we said before, it's this and this is equal because they are equal. So once we cancel out our units and we multiply 8.50 by 2.54, we get the conversion from inches to centimeters. So our given unit multiplied by our conversion factor with our desired unit as numerator and the given unit as in inches in the denominator, we get our desired unit. So in general, we have a desired unit and we have a given unit and we have a conversion factor. Our conversion factor is our desired unit at the numerator and the given unit as the denominator. And once the given unit, they cancel out each other. And so we get our desired unit. So let's go back to what we were saying here. Our given unit or desired unit in numerator, and we get our desired unit and our given unit as the denominator here. All right, so just to repeat, this is our general formula. Given unit multiplied by our desired unit divided by our given unit is equal to our desired unit. All right, so let's look at another question. So in lecture 2, you calculated the wavelength in centimeters. So I'm asking you to convert the centimeters to nanometer. So this is our conversion factor. 1 centimeter is equal to 10 to the 7 nanometer. So we have our centimeters and we have our conversion factor. So we're going from centimeters to nanometer. So take a second and attempt this question. All right, so let's use the same principle that we're working with. Our given unit is centimeters. Our desired unit is nanometers. Our conversion factor is 1 centimeter is equal to 10 to the 7 nanometers, right? So because we're trying to get rid of centimeters, it's in the denominator, right, of the conversion factor. And we're multiplying that by our given unit, right? And then, of course, we have our desired unit here as the numerator. So once we do this calculation, we get 434 nanometers, which has 3 significant figures, 1, 2, 3 here, and we keep the same significant figures in the product. So that's all for now. See you in the next lecture. Thanks for watching.